Hello and welcome back to Chapter 2. Today we're going to look at Section 2.5, which deals with zeros of polynomial functions. This is going to be a two-part video, so we'll start out with 2.5 today and then we'll finish up with 2.5 tomorrow. Now, before we begin, the thing that we're going to look at in this section specifically is how to find all of the zeros of a polynomial function. Now, the zeros of a polynomial function that we're going to identify could be either rational, irrational, or complex zeros. Up until this point, we've talked about how if we have an nth degree polynomial, that we can have at most n real zeros. In other words, if I have a third degree polynomial, I know at most I can have 3 real zeros. Now, I don't have to have 3, but I can have up to 3 real zeros. Now, since we talked about the complex number system in Section 2.4, we can actually improve this statement. When we use the complex number system, if we have an nth degree polynomial, we know that we have exactly n zeros, and that's because we can have both complex or real zeros. So to help us with that, we're going to use what we call the fundamental theorem of algebra. And it says if the function f is a polynomial of degree n, and n is greater than 0, then the function has at least one zero in the complex number system. And we'll look at an example of this here in just a second, but right now I want you to use what we just read about in the fundamental theorem of algebra, and keeping in mind that zeros and factors are really the same thing. Because when we keep all of that in mind, we actually come up with what we call the linear factorization theorem. Now, the linear factorization theorem says if the function is a polynomial of degree n, then f has precisely n linear factors. And remember that something like this is considered a linear factor. Your c sub 1, c sub 2, c sub 3, these are what we would call complex numbers. Now, we learned about the fundamental theorem of algebra. We learned about the linear factorization theorem. However, the two of these theorems will only tell you that the zeros of a polynomial exist. They do not tell us how to find them. And because they tell us that something exists but not how to find them, this is what we call an existence theorem. And we will learn methods of how to find the zeros here shortly. For example 1, we are to find all the zeros of each function. For part A, we see that we have a linear function or a first degree function. And because it's a first degree, we would expect that we'd get 1 0 at most. So if I take this function and set it equal to 0, I end up with x equals 4. So I get exactly 1 0. Now for part B, I have x squared minus 4x plus 4. To find my zeros here, I can actually factor this into x minus 2 times x minus 2. Now this is a second degree polynomial. I do have 2 zeros, but I'm going to have to use that multiplicity rule where, because both of these factors are the same factors, I'm going to end up with x equals 2 as my 0, but I have a repeated 0 because I have 2 of these. And if you wanted to, you could write it as x equals 2 and x equals 2 again. However, just to write it once is sufficient enough. For part C, we have f of x equals x cubed plus 9x. And if we wanted to, we can go ahead and factor this. So we're left with x times x squared plus 9. So to find my zeros, we end up with x equals 0. And if I take x squared plus 9 and set it equal to 0, we end up with x squared equals a negative 9, or x equals plus or minus the square root of a negative 9. In the last section, we learned that we could rewrite that as plus or minus I times the square root of 9, which was 3. So I really end up with plus or minus 3i as my solutions. So all of my zeros would be, or the three zeros would be at x equals 0, x equals a positive 3i, and x equals a negative 3i. And finally, for part D says f of x equals x to the fourth minus 16. Well, I really have the difference of two perfect squares, so I'm going to factor that into x squared minus 4 times x squared plus 4. I can rewrite x squared minus 4 into x plus 2 times x minus 2, and I still have my x squared plus 4. Well, when I go and I set my factors equal to 0, this is going to give me x equals negative 2. I get positive 2, and then for this factor here, I have x squared equals a negative 4. So again, if I square root that, I end up with x equals the square root of a negative 4, which is equal to plus or minus 2i. So my zeros then are x equals plus or minus 2 or plus or minus 2i. So again, as you'll see, I have 4 solutions right here for a fourth degree polynomial. I found 3 zeros at x equals 0 and then plus or minus 3i for my third degree polynomial. And for part B, I have 2 zeros. Even though they're repeated zeros, I still have 2 zeros for my second degree polynomial. So once we've determined how to identify how many zeros we have, we now need to go ahead and try to start figuring out what our possible rational zeros can be. So to help us kind of find what our rational zeros are, we can use what we call the rational zero test. And the rational zero test says, if a polynomial has integer coefficients, then every rational zero of the function has the form. Now we use the notation p over q, or p divided by q, where p represents the factors of our constant term, or the term without any variables, and q represents the factors of the leading coefficient. And again, this is only going to list the possible rational zeros, not the exact rational zeros. So example 2 says to find the rational zeros of the function x cubed minus 5x squared plus 2x plus 8. And in all honesty, when I'm looking for my rational zeros, I don't really care about the middle terms. The terms that are most important to me are the first term and the last term. So to use our rational zero test, we're going to use p divided by q. Now p is going to be the factors of our constant term, or in this case it's 8. So factors of 8, we're going to come up with this by going plus or minus 1. And it will always be plus or minus whatever your factors are. So that gives me plus or minus 2, plus or minus 4, and plus or minus 8. And then I'm going to divide it by the factors of my leading coefficient. Well, in this case, my leading coefficient is really a 1, so it's just plus or minus 1. So to find my rational zeros, I'm going to go ahead and divide this out, and because my q value or q factors are just 1, I really have 1 divided by 1, which is going to give me plus or minus 1. Then I have 2 divided by 1, which is plus or minus 2. 4 divided by 1 is going to give me plus or minus 4. And 8 divided by 1 is plus or minus 8. So if you look at this, you have a total of 2, 4, 6, 8 different zeros, which is kind of a lot, especially if you're going to have to hand test each one of these, but it's a lot more narrow of a field when you consider that you just went from an infinite number of numbers down to just 8. Now, at this point, what I would probably do is I would probably grab my calculator, graph this function right here to identify at least one of your zeros. I don't mind that you do that, but I do want to see the work that is entailed to come up with the rest of your zeros. So when I graph this on my calculator, I see that one of my zeros is at x equals 2. So what I'm going to do then is I'm actually going to use synthetic division to find the rest of my rational zeros. So for my synthetic division, I'm going to use my factor of x equals 2, and I have 1, -5, 2, and 8. And I'm going to bring down my 1. This gives me 2, -3, -6, -4, -8, and 0. So now with my factor of x minus 2, I also have x squared minus 3x minus 4. So if I factor this down, I have x minus 2 times x minus 4 times x plus 1, and that gives me zeros, or rational zeros, at a -1, a +4, and a +2. And if you come back up here to your list, you'll see that your -1 fell within this right here, your +2 fell within this range, and your +4 fell within this range. So the only number that we truly didn't use was the 8. Let's go ahead and do the same thing for example 3, where we want to find the rational zeros of x cubed minus 15x squared plus 75x minus 125. First thing we're going to do is we're going to use our rational zero test, and we're going to take our p and divide it by q. P is going to equal the factors of our constant, which is 125. And don't worry about whether it's a positive or negative. We just want the number itself. So I have plus or minus 1, plus or minus 5, plus or minus 25, and plus or minus 125. And I'm going to divide that by the leading coefficient, which again is 1. So plus or minus 1. So what this tells me then is my possible rational zeros are going to be plus or minus 1, plus or minus 5, plus or minus 25, or plus or minus 125. So again, I have 8 possibilities to choose from. When I graph this on my calculator, I see that I have a 0 at x equals 5. And then I'm going to go ahead and do synthetic division to see if I have any other zeros. So I have 1, -15, 75, and -125. If I bring my 1 down, that's going to give me 5, -10, -50, 25, 125, and 0. So I have factors of x minus 5 and x squared minus 10x plus 25. So if I factor that, I have x minus 5 times x minus 5 times x minus 5, and this gives me the quantity of x minus 5 cubed, so I have a multiplicity of 3, which also tells me that I have 1 0 at x equals 5, and again, if you graph this, you will confirm that. So in this case, out of all my possible rational zeros, I only used one of them. Now in example 4, we're going to find the zeros of 2x to the 4th minus 9x cubed minus 18x squared plus 71x minus 30. This problem here is very similar to what we did in examples 2 and 3. The only exception is now I have a coefficient of 2 instead of 1. Now, if you have a leading coefficient of 1, it's pretty easy. And it's not that much more difficult to have a leading coefficient of something else. It just is going to expand our list of possibilities by quite a bit. So let's go ahead and start out by listing our possibilities of our rational zeros by using the rational zero test, which is P divided by Q. So factors of 30 are going to give me plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 5, plus or minus 6, plus or minus 10, plus or minus 15, and plus or minus 30. Then we're going to divide it by our factors of our leading coefficient, which in this case is 2. So that's going to give us plus or minus 1 and plus or minus 2. So now if I go through and I actually list out all the possible rational zeros, I'm going to take every term up here divided by 1 and then do the same thing where I take every term again and divide it by 2. That's going to give me the total list of possibilities. So let's go ahead and do that. So it gives me plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 5, plus or minus 6, plus or minus 10, plus or minus 15, plus or minus 30. Now that takes care of our dividing by 1. Now I have to do the same thing with 2, and this is all really one continuous list. However, due to space, I'm going to write a second row. So now I'm left with plus or minus 1 divided by 2, which is 1/2. Then I have plus or minus 2 divided by 2, which is 1, which I've already got that right here, so I don't have to relist it. Then I have plus or minus 3/2, plus or minus 5/2, plus or minus 6/2 is really 3, and I've got that right here. 10 divided by 2 is really 5, and I've got that right now. So now I'm up to plus or minus 15/2, and then plus or minus 30/2, which is 15, and I've got that right there. So this right here is a list of all my possible rational zeros. And as you'll see, that gives us 2, 4, 6, 8, 10, 12, 14, 16, 18, 22, 24 different possibilities. So now, let's grab our calculators and pull out at least one zero so that we can go ahead and calculate the rest of them. Now on my calculator, I just see that I have a 0 at x equals 5. So I'm going to do synthetic division. I'm going to bring my 5 out up front, and I have 2, -9, -18, positive 71, and a -30. Doing synthetic division, this is going to give me 2, 10, 1, 5, -13, -65, 6, 30, and a remainder of 0. So now when I write my factors, I end up with x minus 5 times 2x cubed plus x squared minus 13x plus 6. I can't group that. It's not going to factor very well. So what I'm going to do now is I'm going to take this piece right here and pull out a 0 either from your original graph that you already had, or I'm going to just graph this piece and find a 0 of this and do synthetic division again. So when I do that, I'm going to use now that x is equal to 2. So when I do synthetic division, I have 2, and again I'm going to use just this little bit right here. So I have 2x cubed, 1x squared, negative 13x, and 6. So I'm going to bring my 2 down. That's going to give me 4, 5, 10, negative 3, negative 6, and 0. So now my factors are, I still have that x minus 5 from up here. I just created this x minus 2. And now I have 2x squared plus 5x minus 3. And now looks like I can factor this piece right here. So my factors are going to be x minus 5, x minus 2, and I'm going to have a 2x and an x. Because I have a negative 3 and a positive 5, my choices are going to be 3 and 1 on the outside, but it looks like I need to have my 3 right here and 1 here, this being positive and this being negative. So that when I multiply negative 1 times 3, that gives me my negative 3. This is going to give me my positive 6 minus 1 still gives me a positive 5. So now what I found is I have x equals 5, 2. This here is going to give me 1/2 and a negative 3. So in this case, I really had 4 real zeros. And if we go back up to that list from up above, you'll see that our 5, our 5 was right here, our 2 was here, our 1/2 was here, and our negative 3 fell within right there. So our rational zero test did a good job, and so did synthetic division. For example 5, we're right on the same path as what we have been for the last few examples. It says to find all real solutions of x cubed minus 7x squared minus 11x plus 14. Now remember, solutions are really the same thing as a 0 or an x-intercept. So what I'm going to do with this one is, again, I'm going to use my calculator to help guide me. Actually, after I do my rational zero test. My rational zero test tells me to do p divided by q. So I end up with plus or minus 1, plus or minus 2, plus or minus 7, and plus or minus 14, all divided by plus or minus 1. So that's going to give me a list of plus or minus 1, plus or minus 2, plus or minus 7, and plus or minus 14. So I have 8 different possibilities. Now I'm going to get my calculator out, graph it, and see that I really have a 0 at x equals a negative 2. Now this is the best 0. I see I have 2 more, but they're not exact values, so that's why I chose this one right here. So now if I use my synthetic division, I end up with 1, negative 7, negative 11, and 14. Negative 2 times, bring that 1 down. That's going to give us negative 2, negative 9, 18, 7, negative 14, and 0. So what that tells us is our factors are x plus 2 times x squared minus 9x plus 7. Well, I don't have factors of 7 that will add or subtract up to give me 9, so I know that I can't factor that. But what I can do is I can use my quadratic formula. So to do that, and I'm just going to look at this piece right here first, and then we'll deal with that x equals a negative 2 here in just a second. So quadratic formula tells me to take the opposite of b. So I'll have the opposite of a negative 9 plus or minus the square root of a negative 9 squared minus 4 times a, which is 1, times c, which is 7. I'm going to divide all of that by 2 times a, which in this case is 1. So when I simplify, we end up with 9 plus or minus the square root of 81 minus 28 divided by 2, which gives us 9 plus or minus the square root of 53 divided by 2. So my zeros are at x equals a negative 2, and if you want to write it as the exact value, you can go 9 plus the square root of 53 divided by 2, and 9 minus the square root of 53 divided by 2, or you can type these into your calculator and get an approximation. And if you do that, these two here work out to be a decimal of 0.859-ish and 8.14-ish. But these right here are the 3 real zeros of our cubic function. And that's going to conclude the first part of 2.5. We'll see you guys later for the second part. Have a good night.